Okay, now we're going to do table 3, which is the table of initial rates. Okay. In order to figure out what to analyze the kinetics of this experiment, we need to have the rate law. So to do that, we need to figure out what the rate is. So we're going to go through this table to figure out what the rate is. So again, we have 5 experiments, all done at room temperature. The first thing we're going to do, this one's not so obvious, is we're going to figure out how much H2O2 was used, how many moles of H2O2 was used. Okay. The idea here is we're trying to figure out what the change in concentration of H2O2 was during the reaction. Remember, the H2O2 is reacting with Ki, right? So I've written it here as I minus. Potassium iodide, when you dissolve it into water, it gives you I minus. So the peroxide, the H2O2, is reacting with the I minus in a 1 mole of H2O2 for every 2 moles of I minus. So we're going to figure out how many moles of H2O2 are reacting in a given amount of time, and then that will tell us what the rate is. Okay. So here's that equation, but the way we did the experiment was we added one other reagent, which doesn't appear in the rate law, and that is the sodium thiosulfate, or S2O32 minus. So what that's doing is it's acting like a limiting reactant. It's keeping the color from changing for a period of time till it disappears, till it's all reacted. Once it's all gone, then I2 will very rapidly build up and it'll change the color because the I2 reacts with the starch, okay? So it's not intuitive necessarily how we're figuring this out, but the important point of it is that what we do is we say that for every mole of H2O2 that's used or reacts, that corresponds to 2 moles of S2O32 minus the thiosulfate based on these first 2 equations here, okay? So what we're going to do is we're going to figure out how many moles of H2O2 were used from the moles of S2O3. Now, luckily, in table 2, we know how many moles of S2O3 were used because it's right here, initial moles of Na2S2O3. We're going to use it as the limiting reactant, which means that it will all be used up each time. And notice in each experiment, it's the same amount, 0.001 moles. So I'm going to come back over to table 3. And I'm going to do a little calculation. I'm going to say the moles of H2O2 used is equal to the moles of Na2S2O3, thiosulfate. Okay. And I'm going to come back over here and say times 1 mole of H2. So I'll put that in parentheses. 1 mole of H2 for every 2 moles of Na2S2O3, or just S2O3. Okay. And look what you get. You get 0.0005, which makes sense. You should use half as much H2O2 as you use Na2S2O3. And then same idea. We can just scroll down. Oops. There we go. And notice it's the same every time. The reason it's the same every time is the way we calculated was we took the initial moles of S2O3, and that's the same every time. We put in the same amount every time, and then that's multiplied by a half. So if you multiply a half every time, you can get the same value. Now, if you recall back from the earlier table, we also know the volume was a half a liter. So I'm just going to write equal 0.500, half a liter, right? 500 ml. Same thing, we can just drag that down, and that's what the volume is. So now we're going to figure out what concentration change there was during that time period. So from the time that you added the last reagent, the hydrogen peroxide, to the time that it changed color, some concentration change of hydrogen peroxide took place. And the way you calculate that is you just take the moles that were used, the moles that reacted, and divide that by the volume of the solution, and that will give you concentration. Same thing, come on down. It's actually going to be the same every time. Now, what's not the same every time is the time, right? This is the data that we actually did in the experiment, right? So you have your own set of data, which are the average values for your experiment. But let's go ahead and I'm going to give you the times here for this demonstration. You'll have your own values from your own laboratory experience. So I'm going to put in very round numbers, 500 seconds, 245 seconds, 180 seconds, 94 seconds, and then 48 seconds. Okay, so I'm just making those times up. They should roughly be similar. You should see a pattern of the largest time, the slowest is here, and then the fastest is here. And again, the reason it goes that pattern is because in the first experiment, both concentrations are at their lowest values, both reactants, Ki and H2O2. By the time you get to experiment 5, they're at their maximum concentration, so the rate should be faster. To figure out the initial rate, and this is really the initial rate of the reaction, but I'm just going to call it rate, molarity over seconds, right? So you just take the concentration change divided by the change in time. So that would be concentration change divided by time. Okay, let's go ahead and go there. Now, what I see here is, you have a bunch of numbers here. They're pretty small. There may be a way to format this using, so for example, scientific notation. So if I go up to this little 1, 2, 3 for number formats and go to scientific notation, that's a little nicer looking, right? What this is saying is 2.00 times 10 to the minus 6. Okay. Now, those have 3 significant figures, which is probably about right. That's probably what you want. If you wanted to have more significant figures, you could do this, and it'll just, it'll round it. It's just changing the way it rounds it, right, for the display. That's a lot of digits. We don't need that many. I think 3 is probably fine, right? So 1.06, for example. Okay. So there you go. So that's how we're figuring out the rate. Remember, the rate is the change in concentration over the change in time. We're using hydrogen peroxide as the concentration that we're measuring. We could have also done Ki. That's perfectly fine. But we're going to use the hydrogen peroxide for this.